Okay, here's what we're going to assume in section 1.7. We're going to assume that population changes only due to births and deaths. Well, how else could population change? Alien abduction, immigration and emigration. Yeah, so we're eliminating those. We're just doing life and death situations here. So we're talking about a closed group of bacteria, perhaps, that are locked in a petri dish. No more bacteria can get in, no can get out. They multiply or they die. Okay, in that situation, we're going to let beta of t equal the number of births per unit of population per unit of time. And similarly, we will let delta of t be the number of deaths per unit of population per unit of time. In any time interval, delta t, the change in population will then be close. Not just b of t minus delta t, but you got the right idea. It's the number of births minus the number of deaths. The number of births will be beta of t times the population at time t times delta t, because of the way we define beta. Beta is the number of births per unit of time, so I got to multiply by the unit of population, and then per unit of time, so I got to multiply by time. And similarly, we would subtract the number of deaths. The total number of deaths would be delta of t times p of t times delta t. Which of course gives us the change in population is beta of t minus delta of t times p of t delta t. Dividing both sides by delta t, we have delta p over delta t is beta of t minus delta of t times p of t, which looks just like what? It looks just like a differential equation. If we let t go to 0, we get dp dt equals beta of t minus delta of t times population. We get a differential equation.
So is that minus beta or just beta?
That's minus. Births minus deaths.
That's minus beta? Minus beta.
Beta minus delta.
Okay.
Births minus deaths. If beta and delta are constants, then this equation becomes dp dt is some constant times p of t. What kind of equation is that? That's k, yep. dp dt dp dt equals k times p of t. What kind of equation is that? Linear, homogeneous. Separable? Why is it separable? I can divide by the p and multiply by the dt, and I have all the p's on one side, all the t's on the other. It's separable. And you solve that separable equation. You get the population formula that you dealt with back in pre-calculus. You get P of t equals P0, which is the starting population, e to the kt. Problem number 10. This is an example where beta and delta are not constant. It says, suppose that the fish population, P of t, in a lake is attacked by a disease at time t equals 0, with the result that the fish cease to reproduce, so that the birth rate is 0, and the death rate delta, deaths per week per fish, is thereafter proportional to 1 over the square root of p. If there were initially 900 fish in the lake, and 441 of them are left after 6 weeks, how long did it take until all the fish in the lake die? It's number 10 on page 82. Okay, so here's what I think we know. Birth rate is 0. The pollution causes the fish to no longer be able to reproduce. And the death rate, it said, was proportional to 1 over the square root of p. How do I write proportional to 1 over the square root of p?
K 1 over square root of p.
K times 1 over square root of p. It further went on to say that the initial population was 900 fish, and there were 441 left in 6 weeks. P at 6 weeks. T is in weeks. For this problem. All right, so our differential equation was dp dt was births minus deaths times p. In this case, that becomes what's births minus deaths? Zero minus k over root p times p, which is minus k square root of p. P divided by square root of p is square root of p. What kind of equation is that?
Separable.
It's separable. I can write this as dp over the square root of p equals minus k dt. Integrate. What's the integral of dp over the square root of p? It's 2 square root of p. Because this starts as a p to the negative 1/2. I add 1 to my power, it becomes a p to the positive 1/2, which is square root of p. And then I'm going to divide by 1/2, which is the same as multiplying by 2. And this side over here, negative kt plus c. Okay, so square root of p is negative k over 2t plus c over 2. And p would therefore be negative k over 2t plus c over 2, whole thing squared.
Is there a point to doing c over 2? Wouldn't that become c?
You could just write it as c, sure. That's usually what we do, I agree. Don't know why I decided to write it as C over 2 this time. Just to confuse you, I guess. All right, so notice, though, we have how many numbers, don't we know? 2. But the good news is they gave us 2 conditions, didn't they? So we'll plug these in. I'll plug in 0, 900. If I plug in 0, 900, I get 900 equals C over 2 squared square root of both sides. What's the square root of 900? 30. 30 equals C over 2. C is 60.
So if we had just made C, C over 2 is C, we would still have gotten C equals 30.
Yep. Yeah, but it's going to balance out because we have the K over 2 also. Wouldn't matter, it would all balance out in the end.
So I'm going to leave mine on 30.
Because K was just a number 2, so I could have just left it as K. Right? Anyway, it's all going to work out in the end. As long as you're consistent. So P equals negative K over 2T plus 60 over 2 is 30.
Wouldn't it be 4 because it's squared?
Wouldn't what before?
C over 2.
No, because what I did is I took this equation and I did square root on both sides. So I got rid of the squaring, so I didn't have to square the bottom. Okay, now we plug in our other initial condition. That's 6, 1, 441. That gives me 441 equals minus 3K plus 30 squared, because when I plug in 6 over 2 is 3. Square root on both sides there. What's the square root of 441? I think it's a nice number. 21? 21 equals minus 3K plus 30. Subtract the 30, that's negative 9, divide by 3, K is 3. Alright, so my population formula is minus 3/2 T plus 30 squared. Now I'm ready to answer the question. The question was, what was the question? Anybody remember?
How long it would take for all the fish to die?
When do all the fish die, which means population would be 0. So 0 equals minus 3/2 T plus 30 squared. Squared doesn't really do anything because I can square root both sides. 0 equals minus 3/2 T plus 30. Subtract the 30, divide by negative 3/2. T is, what'd you say, 20?
Yeah. This would be negative 30 times 2, which would be 60 divided by negative 30.
I agree. T is 20. It's going to take 20 weeks for all the fish in that lake to die. The logistic model. In many situations, the birth rate doesn't necessarily stay constant. In many situations, as the population grows, the birth rate starts to slow down. How come?
Because people can't afford to have as many kids, maybe, or overcrowding.
There's lots of reasons. People can't afford to have kids. There's overcrowding, which can happen with people or bacteria or animals.
You live in China, the government says no, you can only have
You can become China, the government says no. Right? That's a pretty extreme example. But I suppose it does have lack of resources, lack of food in particular. food, water, all sorts of things. So in a lot of cases, when population grows, the birth rate starts to slow down. So we're going to suppose birth rate is a linearly decreasing function. So we're going to write beta equals beta 0 minus beta 1t. So that's a linearly decreasing function. Why? And well, it's linearly decreasing as long as beta 0 and beta 1 are both positive. Furthermore, we're going to assume delta is constant, just to make things a little bit easier here. Under those conditions, our differential equation takes this form. dp dt was beta minus delta times p. So that's going to be beta 0 minus beta 1t minus delta all times p. Typically, we rewrite that a little bit. I'm going to write it as beta 0 minus delta minus beta 1t times p. So why did I do that? Why did I just switch the order on these two? Any good reason? Oh, I made a bad mistake. This shouldn't be a T. That should be a P. Because it's based on the size of the population, not based on the time that goes on. It's decreasing, linearly decreasing based on the size of the population, not based on the time proceeding. So that makes make a lot more sense, actually. Why did I switch the order of those two?
Because decreasing population.
Yes, but more what I was looking for is this one here, these two things are just constants, these are just numbers. And this one is being multiplied by a p. So these two are a constant, so I'm just going to give them another name. Pick a name I like a lot. I'm going to call this A minus BP times P. Which is AP minus BP squared, where A is beta 0 minus delta, and B is beta 1. All right, so we got lots and lots of letters in this example. And then it gets even worse. This is quite often written this way, and we'll see why we want it written this way in just a minute. This is K times P times M minus P, where K is B, which was beta 1, and M is A over B. So basically we took this and we divided everything by B, we factored a B out, and that would be beta 0 minus delta over beta 1. Alright, so ugly, complicated, it's about to get better. Big question is, what kind of differential equation is that? Separable. Why separable?
Because you can move stuff around.
I can divide by the P and divide by the M minus P, and then I have all the P's on the left, and I can multiply by the dt. It is separable. The hard part would be we would have dp, we would have a P times M minus P on bottom. How would you integrate that? You would have, if you separate your variables, you'd have dp over p times m minus p equals k dt. How do you integrate that left-hand side? Good news is I'm not going to make you do it, but how would you do it? You could use Wolfram Alpha, that's true. You could pray first. I don't know that ever hurts. This has a denominator that factors. Anytime you have a denominator that factors, that's partial fraction. This is a partial fractions problem. The good news is I'm just going to tell you the answer. You integrate when you're going to have a p on bottom and an m minus p on bottom, which is going to give you logarithms there. So you're going to have to exponentiate. When you do all that, you get m p0 divided by p0 plus m minus p0 e to the negative k m t. Nice. Pretty function. All right, now this kind of function has a special form. M times P0, that's just a constant, correct? M and P0, these were numbers. This is a constant. This is a constant. Here's your only variable. Right here, this T. This is called a logistic equation when you have a constant divided by constant plus constant e to the power. Anybody know what those kind of graphs look like? Not a kind of graph you see very often before differential equations. You have no idea? All right, so these kind of graphs tend to look like this. Where you have a horizontal asymptote. So this is your starting population. And what happens is your population at first grows exponentially. But then there comes a point where you reach right about here, and this point has a special name. Anybody know the special name for that?
It's the point where it goes from positive to negative. Concave.
It's the point where it's going from concave up to concave down. Inflection point. Close, not critical point. Critical point is where derivative is 0. This is the point where second derivative is 0. This is the inflection point. It's also in a business setting called the point of diminishing returns. Because if this were money, your money is increasing very, very quickly till you get to here. Here your money continues to increase, but it starts to slow down. So in business, they call the inflection point the point of diminishing returns.
Point of no return.
No, not no return. Diminished point of no return would be when you're hitting the axis. That's the bad point. Point of diminishing returns. All right. So now the question is, if this is the starting population, where's the asymptote? So what's going to happen when t gets to be a very, very big number? When t is a very, very big number, what's e to this power going to be when t is very, very big? Except it's going to be a negative infinity, isn't it?
Yeah.
So when t gets really, really big, what's e to the negative infinity get really, really close to? 0. This gets close to 0. So this is a 0. Then what else happens?
There's just m p over p.
So does that.
Those cancel out.
Because if the e goes to 0, then that makes the m minus p go to 0. Right?
It's not just zero. It's just p0.
Did I copy something off? Because we're supposed to get, the whole thing is supposed to cancel out, and we're supposed to get m.
Yeah, it does.
The whole thing reduces to m?
Yeah.
No, it reduces to p0.
It reduces to p0, doesn't it?
No.
Yes.
E goes to 0, which makes m minus p sub 0 go to 0, and then you have m of p sub 0.
All right, yes. All right, see, everybody goofs up every now and then. This goes to 0, so I was covering it up, and then I was pretending that it was the number 1. It's not the number 1, it's the number 0, which means the whole thing goes away. We're left with M. So that's why when we rewrote this back up here, we started with betas and beta 1 and beta 0, then we went to A's and B's, then we went to K's and M's. That's why we wanted that M right there. M turns out to be the carrying capacity is what it's called. So M is in theory the maximum amount of objects that can live in this environment, whatever the objects may be. Questions on that?
Are we going to have a lot of word problems on this?
How many would you like?
None?
So
That's our carrying capacity.
That's your carrying
the
capacity.
formula K times M minus P be the one that we should put on our note card then, out of all those?
If I were putting a formula on your note card, I would put this one on it.
Okay.
Because I'm not going to make you derive the whole formula. You're just going to need the answer in the end.
Okay.
So that's the formula I would put on my cheat sheet if I were building a cheat sheet. All right, so to do problem number 16, to do the type of problem you're going to need out of this section, here are the formulas you're going to need. You need the differential equation, you need the solution of the differential equation, and you need this, and this is the result from problem number 15. Okay, so that's all the information you need to do problem number 16. Okay, so problem number 16 says, consider a rabbit population satisfying the logistic model. If the initial population is 120, so that's P0, and there are 8 births per month and 6 deaths per month at time 0, so that's your birth at 0 and deaths at 0. So the births at time 0 were 8 and deaths were 6. How many months does it take for P of t to reach 95% of the population?
Like what?
95% of the carrying capacity.
Oh, the
95% of the total allowed population. All right, so what we need to do is here's our solution. We need to find P0. That one's easy. What's P0? 120. We need to find M. M's easy to find. We use this little formula over here. And then we need to find K. All right, so P0 is 120. M is 120 times 8 over 6, which is 160. So we know M, we know P0, the only letter we don't know is K. Well, T is time, that's what we're going to find in the end. How long will it take to reach 95% of our carrying capacity? How do we find K? Any ideas? Use dP over dt. Okay, so I know P. I don't know P. I know M. I know M. Do I know P? I know P naught. Okay, I know P naught. So let's use P naught. This will be time 0. So at time 0, I know P naught. I know M. I know P naught. Do I know dP dt?
It is 0 because there's no change.
Nope. 2. Why 2? 8 minus 6. This is the change in population. The change in population at time 0 would be the births at time 0 minus the deaths at time 0. It would be 2. So you can use the differential equation to find K. So this is, at time 0, our change in population is 2, 8 minus 6, equals K times P is 120 times m minus p. M is 160 minus 120 is 40. So k is 2 divided by 120 times 40, which turns out to be 1 over 2400. All right, so now I have all the information I need. I can plug everything I need into this formula. So I'm going to have P of t is m was 160 times P0 was 120 divided by P0 was 120 plus m minus P0 was 40 e to the negative k times m 1 over 2400 times 160. I got negative t over 15. I got 1/15 for that. All right, so there's my solution to my equation. Now I'm ready to answer the question. How do I answer the question?
Find 95% of 100.
So I have 0.95 times 160 equals 160 times 120 turned out to be 19,200 divided by 120 plus 40 e to the minus t over 15. How do you solve that equation? Well, yeah. I'm going to take, actually what I'm going to do, algebra, that's right. I'm going to multiply by this whole denominator. I'll bring the whole denominator up. 0.95 times 160 was 152. So I have 152 times 120 plus 40 e to the minus t over 15 equals 19,200. All right, then I'm going to do a bunch of steps at once. What would my steps be? Divide by 152, subtract 120, divide by 40. All right, so when you do all that, e to the minus t over 15 is 3/19 is what I got. And then I can use the natural logarithm, so negative t over 15 is ln of 3/19, I mean. Multiply both sides by negative 15, I got t is approximately 27.7. How many months? T must be in months. So in about 30 months, we will already be at 95% of the carrying capacity. Okay, reading like rabbits. So that's what the homework problems in that section are going to look like. You're going to have the formulas all set up. You'll plug in the information. Do a lot of algebra.